This is what quantum physics actually says about death, and it is stranger and more carefully hedged than most videos on this subject will tell you. A Nobel Prize-winning physicist once said, "Matter itself comes from consciousness, not the other way around." A team of doctors in New York recently measured brain activity spiking back to life in patients whose hearts had already stopped, and a stem cell scientist has built an entire theory arguing that death, as we picture it, cannot happen the way we think it does. None of that means the question is settled. What it means is that the line between hard physics and speculation about consciousness is thinner and more contested than people assume. And today, we're going to walk that line carefully, fact by fact, name by name, experiment by experiment. If that sounds like your kind of rabbit hole, hit subscribe, because we go deep into questions like this every week, and you won't want to miss what's coming next. Let's start with the part of this story that isn't in dispute, because before we get anywhere near consciousness and the afterlife, there's a piece of physics so well tested that engineers rely on it every single day. It's called the law of conservation of energy, and it says something almost embarrassingly simple. Energy in a closed system can't be created, and it can't be destroyed. It only changes form. Burn a log, and the chemical energy stored inside the wood becomes heat and light. Explode a stick of dynamite, and stored chemical energy becomes kinetic energy, sound, and a shock wave. Nothing vanished. It just changed clothes. This law has survived more than a century of experimental abuse, tested at scales from subatomic particles to the expansion of the universe itself, and it has never once failed. So here's where people started asking an uncomfortable question. If energy can't be destroyed, what happens to the energy in a human body after death? A commentator named Aaron Freeman turned this into a piece of writing that circulated widely after it aired on public radio, describing what a physicist might say at a funeral, telling grieving parents that their child's energy hadn't disappeared, that every vibration, every unit of heat, every wave that made up that person was still out there in the world, just rearranged. It's a beautiful piece of writing, and it's built on real physics. Right now, at this very moment, your own body is putting out around 20 watts of power through ordinary electrical and chemical activity, roughly enough to keep a dim light bulb burning. When you die, that energy doesn't blink out. It disperses, as heat into the room, as chemical energy into the soil, as motion into the air. There's a companion law worth mentioning here too, because it changes the emotional flavor of this a little. The second law of thermodynamics says that in any closed system, disorder, what physicists call entropy, tends to increase over time rather than decrease. A living body spends enormous amounts of energy fighting that tendency, constantly repairing cells, regulating temperature, maintaining the intricate, highly ordered structure that keeps you functioning as one coherent system instead of dissolving into randomness. Death, from this angle, isn't really energy disappearing at all. It's the moment that fight against entropy stops, and the tightly organized, energy-hungry structure of a living body starts drifting, the way everything in the universe eventually drifts, toward a simpler, less ordered, more spread-out state. The energy is still all there, exactly as the first law demands. It's just no longer being held together in the specific, complicated arrangement that used to be a person. But here's the catch, and it's an important one. Conservation of energy tells you what happens to your energy. It tells you nothing about what happens to you. The heat leaving a corpse is just as real and just as impersonal as the heat leaving a rock that's been sitting in the sun. Physics is completely silent on whether your memories, your sense of self, the feeling of being you, travels along with that dispersing energy or simply stops. That's not a loophole in the science. That's the actual boundary of what the science claims. Anyone who tells you the first law of thermodynamics proves you'll live on in some form after death is taking a real, rock-solid piece of physics and quietly smuggling in a conclusion it was never built to support. Keep that distinction in your back pocket, because we're going to need it again and again as this story gets stranger. Now let's go where things actually do get strange, because quantum mechanics, the physics of the very small, behaves in ways that still make trained physicists uneasy more than a century after it was discovered. The clearest window into that weirdness is an experiment that's over 200 years old in its original form. Back in 1801, a scientist named Thomas Young fired light through two narrow slits cut into a barrier and watched what landed on a screen behind it. If light behaved like a stream of tiny bullets, you'd expect two bright stripes, one behind each slit. Instead, Young saw a whole pattern of alternating light and dark bands, the signature of waves overlapping, reinforcing each other in some places and cancelling out in others. Light, it turned out, behaves like a wave. That would have been a tidy story on its own, except physicists eventually ran the same experiment using individual electrons instead of light, fired one at a time, so there was no way for them to physically bump into each other and create interference the old-fashioned way. And the same striped pattern showed up anyway, one electron at a time, fired alone, somehow still built up a wave-like interference pattern on the screen behind the slits, as though each individual electron were interfering with itself, as though it were passing through both slits at once, and only settling into a single, definite position when it finally struck the screen. That result alone is enough to make anyone's head spin, and it's not speculation, it's one of the most repeated experiments in physics. Then experimenters pushed it one step further, and this is where the story usually goes off the rails in popular science videos, so it's worth being precise here. If you place a detector at the slits to measure which slit each electron actually passes through, the interference pattern disappears completely. The particles stop behaving like overlapping waves and start behaving like ordinary bullets again, piling up in two clean bands. Measuring which path the particle took appears to force it into a single, definite path. This got nicknamed the observer effect, and that name is exactly where the confusion crept in. Because observer sounds like it means a person, watching, and from there, it's a short leap to the idea that human consciousness itself is what forces reality to snap into a fixed state, that nothing is truly solid until a mind looks at it. That idea has genuine appeal, and it's shown up in documentaries, best-selling books, and yes, plenty of YouTube videos. But according to the physics itself, that's not what's happening in the simplest and most common reading of the experiment. An observer, in this context, just means anything that interacts with the particle and extracts information about its position, whether that's a human eye, a video camera, or a simple electronic detector sitting in a lab with nobody watching the readout at all. Run the detector, walk out of the room, and the interference pattern still collapses. Consciousness isn't required for this basic version of the effect. What's required is physical interaction, the kind of interaction that inevitably disturbs a system this small and this sensitive. The mainstream position among physicists is blunt about this. Treating the observer effect as proof that a conscious mind creates reality is a widely repeated misconception, one that even some well-known science communicators have let slip into their explanations for the sake of a good story. There's a more advanced version of this experiment that pushes the weirdness even further, and it's worth walking through carefully because it gets misrepresented online almost as often as the basic double slit. It's called the delayed choice quantum eraser, first built in 1999 by a team of physicists named Yoon Ho Kim, R.U., S.P. Kulik, Y.H. Shi, and Marlon O. Scully, extending an idea the physicist John Wheeler had proposed back in 1978. The setup splits each photon into an entangled pair, sends one down toward a detector screen, and sends its twin off toward a separate set of detectors where researchers can choose, after the first photon has already been recorded, whether to erase or preserve the information about which path it took. And the results are bizarre. Depending on that later choice, made after the first measurement is already in the books, physicists can retroactively sort the earlier data into either an interference pattern or a clean two-band pattern. Online, this gets described constantly as proof that the future can reach back and change the past. It's an understandable read of the raw description, and it's also, according to physicists who've studied the mathematics closely, not what's actually happening. A detailed 2024 analysis published in the journal Quantum Studies, Mathematics and Foundations worked through both Wheeler's original thought experiment and the Kim team's delayed choice quantum eraser, and concluded that every outcome can be fully explained using ordinary, textbook quantum mechanics, with no information from the future required at any point in the argument. What actually happens is subtler than time travel. The full pattern only becomes visible once you sort the data using information from both detectors together, information that couldn't be combined until after both measurements were complete. Nothing physically changes about photons that already struck the screen. It just looks that way if you only glance at half the data. Genuinely strange, still real, still one of the more mind-bending demonstrations in physics. Just not a loophole that lets the future edit the past, and definitely not, on its own, a statement about consciousness or death. There's one more piece of this puzzle worth laying out properly, because we mentioned entanglement briefly already, and it deserves its full history. In 1935, Einstein, together with two colleagues, Boris Podolsky and Nathan Rosen, published a paper with a title that reads almost like a challenge: Can quantum mechanical description of physical reality be considered complete? The paper became known by their initials, the EPR paper, and it laid out a scenario meant to embarrass quantum theory. Two particles interact, then separate, potentially by enormous distances, yet remain described by a single shared mathematical description. Measure a property of one, and you instantly know the corresponding property of the other, no matter how far apart they've traveled. Einstein and his co-authors argued this had to mean quantum mechanics was an incomplete description of reality, because otherwise it implied an influence traveling faster than light, something forbidden by his own theory of relativity. Years later, in a 1947 letter to his friend and fellow physicist Max Born, Einstein used the German phrase that gets translated into English as spooky action at a distance to describe just how uncomfortable this made him. For decades, this stayed a philosophical argument, with no way to settle it experimentally. That changed in 1964, when the physicist John Stuart Bell worked out a mathematical inequality that any theory based on Einstein's assumptions, that particles have definite hidden properties all along, and that no influence can travel faster than light, would have to obey. Quantum mechanics predicted that inequality should be violated. Whoever could actually measure it in a lab would settle the argument for good. That took years of increasingly careful experiments, run by physicist John Clauser in the early 1970s, refined by physicist Alain Aspect in the 1980s to close major loopholes in the setup, and refined further still by physicist Anton Zeilinger in the years after that, closing the remaining gaps and scaling the experiments up to systems with many entangled particles at once. Every single one of these experiments violated Bell's inequality, confirming that entanglement is real and that Einstein's hoped-for hidden variables explanation doesn't hold up. In October of 2022, Clauser, Aspect, and Zeilinger jointly won the Nobel Prize in Physics for this exact body of work, for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. So this isn't old, unsettled, decades-stale physics. It's one of the most recently and rigorously confirmed strange facts in all of science, awarded science's highest honor within the last few years. And yet, even with all of that confirmed, the crucial caveat from earlier still holds completely. Entanglement does not let you send a usable message faster than light, and it does not give two separated minds any way to communicate a thought, a memory, or an intention across space. It's a real, Nobel Prize-winning, deeply strange correlation between particles. It has nothing to do, as far as the confirmed physics goes, with consciousness reaching across a room, let alone across the boundary of death. Before we move into the theories that do put consciousness at the center of things, it's worth understanding why most physicists think the whole consciousness collapses reality idea isn't necessary in the first place, because there's a mainstream, well-developed explanation for why we never see large objects, cats, coffee cups, human brains, sitting around in obvious quantum superpositions, and it has nothing to do with anyone watching. It's called decoherence, and the physicist most associated with working out its details is Wojciech Zurek at Los Alamos National Laboratory, building on earlier work by the physicist Dieter Zeh in 1970. The idea is straightforward once you see it. A delicate quantum superposition can only survive if it's kept almost completely isolated from its surroundings. The instant it starts bumping into stray air molecules, photons, or anything else in its environment, that environment effectively learns information about which state the system is actually in, and the fragile interference pattern that defines a superposition falls apart. Not because anyone consciously observed it, but because the information leaked out into the wider world and became, for all practical purposes, impossible to gather back up. Zurek has described it vividly. A real cat, made of trillions of jostling, warm, wet particles, would never stay in a superposition of alive and dead for even a fraction of a second, because it's constantly leaking information about its own state into the room around it, whether or not a scientist is looking. The same logic applies directly to neurons inside a living brain. Zurek's own analysis states plainly that any quantum superposition among the states of your neurons would be destroyed far too quickly for you to ever become consciously aware of it happening. In other words, according to the physicist who did more than almost anyone to work this problem out mathematically, ordinary decoherence, not consciousness, not a mystical collapse, but simple, relentless interaction with a warm, busy environment, is the leading mainstream explanation for why the world looks solid and definite to us, brains included. It's a serious rival explanation to everything Wigner and the Orchoir theorists proposed. And it's the reason most working physicists don't feel like consciousness needs to be written into the fundamental equations at all. Now let's turn to something different, because so far we've talked about experiments that get misread as consciousness-related when they're not, and about the mainstream explanation, decoherence, that a lot of physicists think makes those misreadings unnecessary in the first place. But there's a separate and much more serious thread in this story, because a handful of genuinely major physicists did, quite deliberately, argue that consciousness plays a direct role in quantum mechanics, not as a misunderstanding, but as their actual, published position. The clearest case is the physicist Eugene Wigner, a Nobel laureate, who in 1961 published an essay called Remarks on the Mind-Body Question. In it, he described a thought experiment that's come to be known as Wigner's friend. Picture a friend of Wigner's sealed inside a laboratory, running a quantum measurement on some system, say, watching for a flash of light that either happens or doesn't. Wigner waits outside. Before he opens the door and asks what happened, what state should he assign to that laboratory? If you follow the standard mathematics of quantum theory strictly, the honest answer is that the lab, including the friend inside it, exists in a kind of blended superposition of both possible outcomes, at least from Wigner's outside perspective, until the door opens and he gets an answer. Wigner found that deeply uncomfortable, because his friend, if you asked her directly, would say she knew the result the entire time, with total certainty, the moment she saw it. From that, Wigner concluded that it must be the entry of the result into a conscious mind, specifically his friend's conscious mind, that actually collapses the wave function, not the physical measurement itself. In Wigner's own framing, observing a system changes its wave function unpredictably because what he called the entering of an impression into our consciousness forces a revision of everything we expect to happen next. This view, sometimes labeled consciousness causes collapse, drew on earlier arguments from the mathematician John von Neumann in the 1930s and the physicists Fritz London and Edmund Bauer in 1939. Wigner even went further, arguing that this made the human body capable of, in a real sense, deviating from the laws of physics as we'd measure them in a purely inanimate object, precisely because a mind was involved in a way nothing lifeless could be. It's worth being honest about where this idea stands today. According to multiple physics sources summarizing the field, physicists have not generally accepted Wigner's argument, and it remains very much a minority position. But it hasn't vanished from serious academic conversation either. In May of 2021, the philosopher David Chalmers from New York University and the physicist Kelvin McQueen from Chapman University published a paper titled Consciousness and the Collapse of the Wave Function, stating plainly that the idea consciousness collapses the wave function was taken seriously by John von Neumann and Eugene Wigner, but is now widely dismissed, while going on to argue that a more carefully constructed version of the theory, combining a mathematical model of consciousness with specific collapse dynamics, remains a live, testable research program rather than something that's been definitively ruled out. So this isn't a case of a fringe internet theory with no real backing. It's a case of a genuinely minority position within physics and philosophy, championed by real Nobel laureates and taken seriously enough by contemporary academics to still generate peer-reviewed papers, while remaining firmly outside the scientific mainstream. It's worth pausing here to bring in Erwin Schrödinger, since his name attaches to the most famous thought experiment in this entire field, the cat in the box that's simultaneously alive and dead until observed. Schrödinger himself, a Nobel laureate whose equation describes how quantum states evolve, wrote extensively and quite personally about consciousness later in his career. In his book, What is Life?, combined with a later essay called Mind and Matter, he wrote, and this is a documented and traceable quote, "Consciousness cannot be accounted for in physical terms, for consciousness is absolutely fundamental. It cannot be accounted for in terms of anything else." Schrödinger was deeply drawn to Vedanta philosophy from India, and in a separate book called My View of the World, he wrote that Vedanta teaches consciousness is singular, that all experience plays out within one universal consciousness, rather than being split up into separate individual selves, and that when a person dies, in this framework, something continues on and takes another form. It's crucial to be precise about what this is. It's the personal philosophical and spiritual reflection of a brilliant physicist, not a physics result, not something derived from his own equations, and not a claim he presented as scientifically proven. He was explicit that this came from ancient wisdom traditions, not from laboratory data. In that same body of writing, Schrödinger also put it this way: "The world is given to me only once, not one existing and one perceived. Subject and object are only one, collapsing the usual boundary between the person doing the observing and the world being observed into a single unified thing." Still, it tells you something meaningful, that one of the actual founders of quantum mechanics, the person whose own equation is the mathematical backbone of everything we've discussed so far, spent real intellectual energy, late in his career, wrestling with exactly the question this video is asking, even while keeping that wrestling clearly labeled as personal philosophy rather than physics. That brings us to the theory most associated with the phrase quantum consciousness in the popular imagination. Roger Penrose is a British mathematical physicist who spent decades working on general relativity and the structure of black holes, and in 2020, he was awarded a share of the Nobel Prize in Physics for proving that black hole formation is a robust, unavoidable prediction of Einstein's equations. This is not a fringe figure with no credentials. This is one of the most respected theoretical physicists alive, and starting in the 1990s, Penrose teamed up with an American anesthesiologist named Stuart Hameroff, who had spent his career thinking about consciousness from an unusual angle, watching patients lose and regain awareness on the operating table as anesthetic drugs were administered and withdrawn. Together, they proposed something they called orchestrated objective reduction, ORS or R for short, first laid out formally in a 1996 paper in the Journal of Consciousness Studies. Their idea, stripped down to its core, is that structures inside brain cells called microtubules, tiny protein tubes that form part of a cell's internal skeleton, might be capable of sustaining quantum computations, and that consciousness itself arises the instant those quantum states collapse, tied to Penrose's own separate ideas about how gravity might force quantum systems to settle into a single definite state. It's an audacious theory. It tries to explain consciousness using a modification to fundamental physics that doesn't exist yet in any confirmed form. 2 years after their original paper, in 1998, Penrose and Hameroff, working with physicists Arthur Eckert and Richard Yoja, published a more detailed version of the mechanism in the Philosophical Transactions of the Royal Society, laying out specifically how quantum superposition and a form of quantum computation might occur inside those microtubule structures, the cylindrical protein lattices that make up part of a neuron's internal scaffolding. And the scientific community's response has been sharp, sustained skepticism. In 2014, a group of researchers, Jeffrey Reimers, Laura McKemish, Ross Mackenzie, Alan Mark, and Noel Hush, published a rebuttal in the journal Physics of Life Reviews, with a title that leaves nothing to the imagination: The Revised Penrose-Hameroff Orchestrated Objective Reduction Proposal for Human Consciousness is Not Scientifically Justified. Penrose and Hameroff published a reply defending their work in that same issue, and the argument has never really been resolved. Then in 2022, physicists running an experiment beneath the Gran Sasso mountain in Italy, using the kind of ultra-sensitive detectors normally reserved for hunting dark matter and neutrinos, tested the simplest version of the gravity-based collapse mechanism that OR depends on. Physics World reported the result plainly. This version of the theory looked highly implausible, though the researchers left open the possibility that more complicated versions of the collapse mechanism might still survive. More recently, in April of 2025, a researcher named James Tagg, working with a private company called Valis Corporation, posted a preprint to Archive claiming that an experiment run on a superconducting quantum computer showed wave function collapse behavior consistent with OR. It's worth being honest about what that word preprint means. It hasn't gone through the full peer review process that established physics findings require, and one experiment from one private lab is a very long way from settling a 30-year-old scientific argument. So where does OR actually stand today? It remains a serious, high-profile hypothesis, taken seriously precisely because Penrose is a Nobel laureate, but it is very much a minority position, disputed on both biological grounds, because nobody has proven the warm, wet, chaotic environment inside a living brain can sustain fragile quantum states long enough to matter, and on physical grounds, because the gravity-driven collapse mechanism it depends on hasn't been confirmed. This is a live scientific debate, not a settled discovery, and any script that tells you otherwise is skipping the fine print. Let's step sideways for a moment into an entirely different quantum idea, one that shows up constantly in death and afterlife content, but that most videos never explain properly, because it comes from a genuinely tragic real-life story that's worth telling in full. Physicist Hugh Everett III completed his PhD at Princeton University in 1957, supervised by John Archibald Wheeler, the same physicist whose delayed choice idea we talked about earlier. Everett's thesis proposed something radical. Instead of assuming the wave function collapses down to one definite outcome when a measurement happens, what if it never collapses at all? What if every possible outcome simply happens, each one branching off into its own separate, mutually unobservable version of reality? A physicist named Bryce DeWitt popularized this years later under the name it's known by today, the many worlds interpretation. The reception, at first, was cold. Everett traveled to Copenhagen to discuss his idea directly with Niels Bohr, one of the founding figures of quantum theory, and by most accounts received a chilly response. Discouraged, Everett left academic physics entirely and went to work for the Pentagon, doing mathematical modeling of nuclear war strategy for the rest of his career. He died in 1982 at 51 years old. His son, Mark Oliver Everett, went on to become a musician, fronting the band Eels, and has spoken publicly over the years about growing up in the shadow of a father whose most famous idea implied an infinite branching tree of alternate realities, most of which he never got to see resolved in his own lifetime. Here's the part of the story that connects directly and painfully to everything this video is about. Everett's daughter, Elizabeth, died by suicide in 1996, and according to biographical accounts, her note said she was going to join her father in another universe. That's a devastating real detail, and it's worth sitting with for a second, because it captures exactly the danger buried inside this whole topic. Everett's mathematics describes a formal structure for how quantum probabilities behave. It was never a promise about where a grieving person's consciousness goes after death, and treating a physics thesis as a literal roadmap to reunion in another branch of reality is a leap the mathematics itself does not support, no matter how emotionally understandable that leap might be for someone in pain. Robert Lanza built his career as a physician and stem cell researcher, respected enough in that field to be named among Time magazine's list of the world's most influential people. But outside the lab, Lanza developed a sweeping philosophical framework he calls biocentrism, first published as a book in 2009 with astronomer Bob Berman, and expanded in 2016 with a follow-up titled, quite directly, Beyond Biocentrism, Rethinking Time, Space, Consciousness, and the Illusion of Death. Lanza's central claim flips the standard scientific story on its head. The conventional view says the universe existed for billions of years before life appeared, that consciousness is simply a late-arriving byproduct of evolution happening inside brains that emerged from a much older, indifferent cosmos. Lanza argues the opposite, that consciousness is the foundation and that space, time, and matter are, in his words, tools of biological perception rather than objective things existing independently out there in the world. He leans heavily on the double-slit experiment as evidence, and he draws on the many worlds interpretation, the same one Everett proposed, arguing that a version of you always continues on somewhere, which is how he arrives at his signature claim that death, as we picture it, is an illusion. In his own writing, Lanza has described life as something like a perennial flower that returns to bloom in the universe, a deliberately poetic image rather than a technical one. His work has attracted prominent admirers outside mainstream physics too. Author Deepak Chopra provided a cover endorsement for Beyond Biocentrism, calling it enlightening, which tells you something about which audience this theory has found its warmest reception with, an audience more drawn to spirituality and wellness content than to peer-reviewed physics journals. It's worth pausing on a review this theory has received from outside its own promotional materials. Sam Wolfe, writing a critical breakdown of biocentrism, points out something that's easy to miss in Lanza's confident prose. Even if the many worlds interpretation turned out to be completely correct, and even if a genuine multiverse existed, none of that would automatically mean that your consciousness, the specific stream of awareness you're experiencing right now reading these words, continues on in another branch after your body dies here. Multiple universes existing is a very different claim from your personal continuity surviving into one of them. It's the exact same gap that swallowed Everett's own daughter's note, just dressed up decades later in different branding. Lanza's framework borrows real, if contested, ideas from physics and stretches them considerably further than the physics itself actually goes. This is a good moment to zoom out and name the broader intellectual territory all of this sits inside, because there's an entire respected field of philosophy wrestling with a version of this exact question, separate from any quantum physics at all. In 1995, the philosopher David Chalmers coined a term that's now standard in the field: the hard problem of consciousness. The easy problems, as he framed them, are things like explaining how the brain processes information or produces behavior, which are difficult but ultimately mechanical puzzles. The hard problem is different. Why does any of that physical processing come with a felt, subjective experience at all, rather than just happening in the dark, with no one home to notice it? Nobody has solved this. Chalmers himself has explored panpsychism, the idea that consciousness, or something like it, might be a basic, fundamental feature of the universe, rather than something that only switches on inside complicated brains, as one possible avenue toward an answer. And philosophers like Philip Goff have become prominent public defenders of that view. This is philosophy, built on logic and argument rather than laboratory experiments, and it hasn't been resolved by consensus. But it's the real intellectual backdrop behind a lot of quantum consciousness content, whether the people making that content know it or not, and it's worth knowing it's there, arguing honestly and rigorously, completely independent of double slits and microtubules. Before we come back to human death directly, there's one more real piece of physics worth including, because it shows the theme of does information ever truly get destroyed, playing out in the most extreme environment physics can describe: a black hole. In 1997, Stephen Hawking and fellow physicist Kip Thorne made a formal bet with Caltech physicist John Preskill. Hawking and Thorne argued that anything swallowed by a black hole has its information permanently and irretrievably destroyed once the black hole eventually evaporates, a direct violation of what quantum theory normally requires, since standard quantum mechanics says information should never be truly erased from the universe, only scrambled. Preskill bet the opposite, that a future, more complete theory of quantum gravity would show the information secretly escapes after all. In July of 2004, at a conference in Dublin, Hawking stood up and conceded the bet. He handed Preskill a baseball encyclopedia, joking that information could be retrieved from it at will, and famously remarked, "Not only does God play dice, but he sometimes confuses us by throwing them where they can't be seen." He later added a darker joke about the whole affair, comparing the practically useless form the information takes once it's escaped a black hole to burning an encyclopedia, and joking that maybe he should have just handed Preskill the ashes instead. It's worth noting the story doesn't end there quite as neatly as it's often told. Kip Thorne, Hawking's original partner in the wager, never actually conceded, and the deeper mathematical mechanism behind how information escapes a black hole is still an active, unsettled area of research decades later. Still, the general direction physicists lean is clear and telling. Even in the single most violent, matter-destroying environment the universe contains, the working assumption among most physicists is that information is not annihilated, only transformed and scrambled beyond easy recognition. That's a strikingly similar shape to the story we opened this video with. Energy that doesn't disappear at death, just changes form. It's a pattern worth noticing, even though, once again, none of it is a direct statement about where your personal consciousness goes. Now let's turn to something entirely different, because everything up to this point has been theoretical physics and philosophy. There's also real, peer-reviewed medical research that studies this exact question from a completely different direction, not asking what quantum mechanics implies about consciousness, but directly examining what happens to the human mind at the actual, clinical moment of death. The modern scientific study of this territory really begins with a specific book and a specific man. Raymond Moody, an American psychiatrist and philosopher, published Life After Life in 1975, based on interviews with roughly 150 people who had come close to death or been clinically resuscitated. Moody coined the very term near-death experience in that book, and he identified a recurring set of elements across the accounts he collected: a buzzing or ringing sound, a sense of leaving one's own body, moving through a tunnel, encountering a being of light, reviewing one's life, and meeting deceased relatives. The book became a massive, decades-spanning bestseller and effectively launched this whole field of inquiry. One of the researchers who took that starting point and turned it into rigorous science was Bruce Greyson, an American psychiatrist who began studying these cases at the University of Virginia in the mid-1970s and continued for nearly 50 years, eventually becoming Professor Emeritus of Psychiatry and Neurobehavioral Sciences there, and leading the university's Division of Perceptual Studies. Greyson has personally studied more than 1,000 cases over his career and developed a standardized measurement tool, the Greyson NDE scale, first published in 1983 in the Journal of Nervous and Mental Disease, now used internationally by other researchers to classify and compare these experiences consistently rather than relying on loose, anecdotal description. In his 2021 book, After, a doctor explores what near-death experiences reveal about life and beyond, and in interviews since, Greyson has been candid that decades of rigorous documentation changed his own thinking, while remaining careful not to overstate what that means. In one recent interview with his university, he put it this way: "Most people who've had these experiences tell him they simply can't put it into words, and he believes them, and so his own honest position is that whatever happens after death, and he does think something does, it's far enough beyond ordinary imagination that speculating about the specifics isn't a productive use of time." That's a scientist's answer, not a salesman's answer. Careful, personal, and openly uncertain about the details, even while taking the phenomenon itself seriously. Meanwhile, in the Netherlands, a cardiologist named Pim van Lommel was pursuing the same question with hospital data. Van Lommel worked at Hospital Rijnstadt in Arnhem from 1977 to 2003, and in 1988 he initiated a prospective study spanning 10 Dutch hospitals, tracking patients as they were resuscitated in real time rather than relying on people's memories months or years later. The results were published in The Lancet, one of the most respected medical journals in the world, in December of 2001. Out of 344 consecutive cardiac arrest patients who were successfully resuscitated, 62 of them, 18%, reported a near-death experience, and 41 of those, 12% of the total group, described what the researchers classified as a deep, core experience. One detail from that paper stands out and remains genuinely unexplained. Patients who had these experiences, particularly the deeper ones, were significantly more likely to die within the following 30 days than patients who didn't report one, a statistical association the researchers themselves flagged without fully accounting for it. Van Lommel later argued, in his own writing and in his book Consciousness Beyond Life, that a purely physical explanation, like oxygen deprivation to the brain, should in theory produce similar experiences in most or all resuscitated patients, since they'd all suffered comparably compromised brain function. and the fact that only a minority reported anything at all struck him as a real gap in the standard neuroscientific account. That's Van Lommel's personal interpretation of his own data, offered honestly as an argument rather than a proven conclusion, and it has been challenged by other researchers on both methodological and physiological grounds since it was published. Which brings us to the most recent and in some ways most rigorous chapter of this research, the work of Sam Parnia. Parnia is a British-American physician who trained at Guy's and St Thomas's Medical School at King's College London and earned a PhD in cellular biology from the University of Southampton, focused specifically on the kind of brain injury that happens during cardiac arrest. He currently directs critical care and resuscitation research at NYU Langone Health, after leading similar work at Stony Brook Medicine. In 2014, Parnia's team published results from a study called AWARE, an acronym for Awareness, during air resuscitation, and it was massive by the standards of this field. A 4-year international study spanning 15 hospitals and tracking 2,060 cases of cardiac arrest. As Parnia put it in the announcement from Stony Brook University, the goal was to move past the vague, emotionally loaded language of near-death experiences and instead explore objectively what happens when we die. Among patients who reported some form of awareness and completed detailed follow-up interviews, the results were more varied and more unsettling than the popular image of a peaceful light at the end of a tunnel. 46% described a wide range of memories that didn't match the classic near-death narrative at all, some of them frightening or distressing. 9% described experiences that did fit the traditional profile. 2% described something closer to a genuine out-of-body experience, with specific recollections of seeing or hearing things that were actually happening in the room. One of those cases, involving a patient who reported hearing specific auditory cues, was validated and precisely timed against the real events in the room, occurring during a documented 3-minute stretch when the patient's heart wasn't beating at all. Then came AWARE-IE, a follow-up study spanning roughly 25 hospitals across the United States and the United Kingdom, run out of NYU Grossman School of Medicine. This time focused on patients who received CPR after cardiac arrest inside a hospital setting between May of 2017 and March of 2020, 567 patients in total. Fewer than 10% of them survived long enough to leave the hospital, which gives you a sense of just how narrow this window into human consciousness actually is to study. But among the survivors, the findings, released in 2022, were striking. About 1 in 5 described a lucid experience of death, something they remembered clearly, despite appearing completely unconscious at the time. And researchers didn't just rely on memory and interviews. They picked up measurable spikes in brain electrical activity, in some cases occurring up to an hour into ongoing CPR, patterns that challenged the long-held medical assumption that the brain suffers permanent, irreversible damage within about 10 minutes of the heart stopping. Parnia himself, quoted in NYU Langone's own materials, described these findings as pointing toward a real, yet little understood dimension of human consciousness that becomes uncovered with death. That's a careful sentence, and it's worth reading closely, because Parnia and his co-authors have been consistently and explicitly cautious about what this research does and doesn't prove. In their own published conclusions, they state directly that the work has neither proved nor disproved the reality or meaning of patients' experiences and claims of awareness in relation to death. That's about as far from a triumphant "we found the afterlife" headline as you can get. And it's exactly the kind of scientific restraint that separates AWARE and AWARE-I, funded in part by NYU Langone, the John Templeton Foundation, the Resuscitation Council in the UK, and the National Institute for Health Research in the UK, from the more speculative territory of biocentrism, or orcho-R. What Parnia's research actually demonstrates, at minimum, is that the brain does not simply flatline into silence and stay there the moment the heart stops. There's a window, longer and stranger than doctors used to assume, where something measurable is still happening, and in a meaningful number of cases, something is apparently still being experienced. Taken together, Moody's original interviews, Grayson's 50 years of careful documentation at a major research university, Van Lommel's hospital-based Dutch study published in one of the most respected medical journals on the planet, and Parnia's large-scale international AWARE studies form a genuine, decades-long, cross-continental research tradition, built by doctors working inside real hospitals with real patients, not by theorists working from equations alone. It's the most empirically grounded branch of this entire topic, and every single researcher in it, when speaking carefully and for the scientific record rather than for a book jacket, has stopped short of claiming they've proven consciousness survives death. What they've shown, repeatedly and across different countries and decades, is that the end of measurable life is not the instant, silent shutdown it was long assumed to be. Before we tie all of this together, it's worth stepping back from laboratories and hospitals entirely for a moment, because none of what we've covered so far is actually new to humanity. People have been grappling with this exact question, whether death is truly an ending, for as long as there's been writing, long before anyone had a word for quantum mechanics, and some of the oldest answers on record hold up remarkably well next to the physics. In ancient Egypt, the dominant picture of death wasn't an ending so much as a test. The Egyptian Book of the Dead, really a personalized collection of spells rather than one single fixed text, describes a ritual known as the weighing of the heart. In it, the god Osiris presides over a divine court, while the deceased's heart, believed to be the seat of memory, thought, and character, is placed on one side of a golden scale, balanced against a single feather belonging to Ma'at, the goddess representing truth and cosmic order. Before the weighing, the dead person recited a list of 42 denials, declaring, one by one, all the specific wrongs they had not committed in life. If the heart balanced against the feather, the person passed into eternal life alongside Osiris. If it didn't, a composite monster named Amit, part crocodile, part lion, part hippopotamus, devoured the heart on the spot, which in Egyptian belief meant a second, final, and much more absolute death, the complete erasure of the person, rather than an afterlife of any kind. It's a strikingly literal, almost mechanical vision of moral accounting, and one of the oldest surviving human attempts to insist that what a person does in life determines what becomes of them afterward. Centuries later, and an ocean of culture away, the Bhagavad Gita, one of the central texts of Hinduism, offered a very different answer, built entirely around the idea that the physical body and the true self were never the same thing to begin with. In the text, the warrior Arjuna is paralyzed with grief on a battlefield, unwilling to fight relatives and teachers arrayed against him, and the god Krishna's response is to explain that the self, the Atman, was never born and therefore can never die. In one of the Gita's most quoted passages, Krishna tells Arjuna that weapons cannot cut this self, fire cannot burn it, water cannot wet it, and wind cannot dry it, describing it as eternal, all-pervading, unmoving, and ancient. Grieving for the dead, in this framework, is described as a kind of category error, mourning something that was never actually destructible in the first place, comparable to grieving over a set of clothes because they've been changed for new ones. Buddhism, which grew directly out of the same broader Indian philosophical world, took the idea of continuation after death in yet another direction, most vividly laid out in a text usually translated into English as the Tibetan Book of the Dead, whose actual title, Bardo Todol, means liberation through hearing during the intermediate state. Tradition credits the text to the 8th century Buddhist master Padmasambhava, though most scholars believe it was likely composed later and rediscovered as a hidden treasure text in the 14th century by a figure named Karma Lingpa. The text describes a sequence of intermediate states, called bardos, that a person's consciousness passes through across a traditional period of 49 days between death and rebirth, first confronting a pure, clear light at the very moment of death, then a series of vivid and sometimes frightening visions representing the person's own accumulated thoughts and actions, and finally drifting, propelled by karma, toward a new birth. Traditionally, a lama or knowledgeable companion reads the text aloud directly to the dying and then to the body afterward, speaking to the consciousness as though it can still hear and understand, coaching it step by step through confusion toward, ideally, liberation from the entire cycle rather than another rebirth into it. Ancient Greek and Roman philosophy took a notably more restrained, almost clinical approach by comparison. The philosopher Epicurus writing in the 4th and 3rd centuries BC, argued in his surviving letter to Menoetius that death simply isn't something a person can ever actually experience, and therefore isn't something worth fearing at all. His reasoning was almost mathematically tidy. All good and bad, to Epicurus, depend entirely on the capacity to sense and feel something, and death is precisely the total absence of sensation, so death itself can never be present to the person it happens to. As he put it, so long as we exist, death isn't here yet, and once death is here, we no longer exist to encounter it, meaning it is nothing to us, neither to the living who haven't met it yet, nor to the dead who no longer exist to be bothered by it. The Stoic philosophers who came after him, particularly the Roman Emperor Marcus Aurelius, in his private journal known as the Meditations, leaned on something that sounds almost exactly like the physics we opened this video with, just phrased 2,000 years earlier and without any equations. Marcus described death repeatedly, across dozens of entries he apparently never intended anyone else to read, as nothing more than the dissolution of the elements from which each living thing is composed, and asked pointedly why anyone should fear becoming part of that constant, ordinary process, given that no individual element seems to suffer any harm from continually converting into other forms. In one especially striking passage, he called death something like birth, a natural mystery, elements that split and recombine, language that lines up almost eerily well with a modern physicist's description of energy simply changing form rather than vanishing, arrived at through patient philosophical reasoning rather than laboratory measurement, roughly 18 centuries before the first law of thermodynamics was formally written down. None of these traditions agree with each other on the specifics, and it would be a mistake to flatten them into one single message, because they genuinely don't converge on the same conclusion. Egypt's vision involves moral judgment and the real possibility of total annihilation for the unworthy. The Gita insists the true self was never mortal to begin with and needs no continuation because it never stopped. The Bardo Todol describes an active, temporary, karma-driven journey measured in specific weeks. Epicurus and the Stoics, by contrast, largely stripped the fear out of the question without promising personal continuation of any kind at all. What they do share, across cultures that had no contact with one another and were separated by thousands of years and thousands of miles, is the same basic instinct this entire video has been circling. A sense, expressed differently in every single case, that whatever a person actually is, doesn't simply switch off into nothing the instant the body stops working, or, in the more austere Greek and Roman versions, that even if it does, that fact alone isn't something worth being afraid of. Quantum physics didn't invent this question, and it hasn't answered it either. It's just the most recent chapter in a conversation humanity has been having with itself for roughly 5,000 years. So where does all of this leave the original question, whether death is an illusion, whether quantum physics has quietly revealed that we don't actually end? Here's the honest, unglamorous summary. The law of conservation of energy is rock solid, and it guarantees that the energy making up your body doesn't disappear when you die, it just changes form, dispersing back into the world around you, in the same broad spirit, though a very different mechanism, as the way physicists now believe even a black hole doesn't truly annihilate the information it swallows. What conservation of energy does not guarantee, and was never designed to address, is whether your subjective experience, your sense of being you, goes along with that energy, or simply stops. The double-slit experiment, the delayed choice quantum eraser, and quantum entanglement, confirmed decisively enough to win the 2022 Nobel Prize in Physics, are all completely real, all thoroughly tested, and all genuinely strange, showing that reality at the smallest scales does not behave the way our everyday intuitions expect. But the versions of these experiments that require a conscious human mind to make reality real, or that require the future to reach back and rewrite the past, are, according to the physics community itself, popular misunderstandings rather than findings written into the equations, especially once you account for decoherence, the mainstream, well-tested explanation for why superpositions vanish through ordinary interaction with the environment rather than through anyone's act of watching. That said, a small number of serious physicists, Wigner most famously, did once argue for something much closer to the consciousness version of events, and a handful of contemporary academics still consider a refined version of that idea worth studying rigorously, so it would be inaccurate to say the question is completely closed, even if it's a minority position by a wide margin. Or is a serious hypothesis proposed by a Nobel laureate and taken seriously enough to be tested experimentally, and it remains sharply contested, unconfirmed, and treated as a minority position within physics and neuroscience. Everett's many worlds interpretation is a mathematically coherent, seriously debated way of doing quantum mechanics without wave function collapse at all, and it says nothing whatsoever about personal continuity after death, a distinction that mattered enormously and tragically in at least one real family's life. Biocentrism takes some of these same real, strange quantum ideas and extends them into a much broader philosophical claim that death is an illusion, a claim its own critics point out doesn't actually follow logically, even if its underlying physics premises were true. Chalmers's hard problem of consciousness reminds us that even without any quantum mechanics at all, nobody, materialist or mystic, has actually explained why subjective experience exists in the first place. And the near-death research tradition, from Moody through Grayson and Van Lommel to Parnia's aware studies, represents something different from all of that. Hard, peer-reviewed, cautiously interpreted evidence that the brain remains more active, for longer, around the moment of death than doctors used to believe, without the researchers themselves claiming that proves consciousness continues afterward. None of that adds up to a clean, satisfying answer, and maybe that's the most honest place a video like this can land. The physics, the medicine, and the 5,000 years of human philosophy and religion, all pointing at this same question, turn out to be a story with several very different chapters running side by side. Some of those chapters are settled, tested, unglamorous science, energy-changing form, information apparently surviving even a black hole in some transformed sense, brains staying electrically active longer than expected. Other chapters are genuinely open, populated by serious scientists, philosophers, priests, and monks across an enormous span of time, all asking serious questions that nobody, including the people asking them, most carefully and most honestly, including Bruce Grayson himself, after 50 years of looking directly at this question, has actually managed to answer yet. What quantum physics actually reveals isn't a proof that death is an illusion. It's a reminder that reality, at its foundation, is stranger and less settled than most of us walk around assuming, and that the honest answer to a question this big is very often, we don't fully know yet, an answer the Egyptians, the authors of the Gita, the Buddhist monks who compiled the Bardo Turdol, and the Stoics in ancient Rome were already circling, in their own very different ways, long before anyone had ever heard of a double slit. If you think about it, that's a far more interesting and far more honest place to end up than a tidy, comforting conclusion would have been.